So, if you remember on Friday we talked about discontinuities, there were two classifications. What were they?
Continuous and non.
Yeah, we had discontinuous and continuous. We specifically had two categories of discontinuities. Non-removable and removable. Remember, the removable was the one that you could put the piece of paper, remove the discontinuity. The non-removable you couldn't. So if you look at this question here, it says determine whether f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. So the first thing you're going to do to determine if it's continuous, you're going to determine whether or not this function is even defined at 2. So to determine whether it's defined at 2, I'm going to plug 2 in here for x. So if I plug 2 in for x, 2 times 2 squared, which is what? 8 minus 1, which equals what? 1. So that in fact does check out. Now the next thing you're going to do is graph that. So on your calculator, I want you to go ahead and graph that.
Wait, what is it? How do you know if it's continuous or not?
First of all, we have a value. Yes.
I don't understand how that all checks out.
Yeah. Like why does
Can you
it?
explain that?
2 times 2 squared is 8.
Uh-huh.
Minus 3 times 2 is 6. Minus 1. 8 minus 6 minus 1 is 1.
Okay, but what does
Okay,
that do?
we're not finished with the problem yet, guys. Okay, first of all, you need to see if you can even get a value. That's the very first thing you're going to do. Now, if you what I just said now, we need to graph it. So go ahead and graph that in.
Graph
Go ahead and graph that function in the z standard window.
the f of x equals
The f of x equals 2x squared minus 3x minus 1. Now, when you graph that, you notice it is what shape? It's a parabola that opens up. Now what I need you to do is go to x equals 2, and I want you to look at x equals 2. Okay? X equals 2 should be somewhere right about here. It's crossing like right at the 0. Okay, now we've got to determine if the function is continuous. So based on the fact that, in fact, the function has a y value, and based on the fact that here at 2 it looks like it's continuous, we can conclude then that the graph is continuous. So determine whether it is continuous. Yes, it is continuous.
So do we really have to do the equation?
Yes, you do need to do the equation because this is the thing for those of you wondering about the equation. If you plugged in a value right away and you got something that didn't work, you could stop and say the function was discontinuous. Okay? So once we got a value here, what we needed to do is then look at the graph just to make sure that the graph was in fact continuous, and then that's based on those two, we can conclude that the graph is in fact continuous. So you have to do both.
So an example of like one not working up there would be like a decimal.
Example of one not working at the very top would be this. Okay, if I were to plug in 0, what do you get? 1 over 0, which is undefined. So you could stop right there. The function is not going to be continuous at 0. So that's an example of where you could stop right away. You wouldn't need a graph. So let's go and look at the next one. F of x equals x cubed. We are going to go ahead and look at that x value of x equals 0. Okay, I forgot to put that in there. This one is x equals 0. So the very first thing you're going to do is you're going to evaluate the function at 0. So if I evaluate the function at 0, what do you get? That equals 0. So that checks out so far. We found a value. So now our next step is to do what? Graph it. Good. So let's go ahead and graph it. And we're going to look at this graph at 0. What do you notice this graph kind of looks like? Swirl, so it kind of looks like this. Where's the 0? Right in the middle, right here. Okay? And so, is this graph going to be continuous at x equals 0? Yes.
Alright, so as long as you plug in and you get a value. Okay, so when you graph that.
No. It has to match with the graph. That's why we have to look at the graph, because there is a possibility it isn't.
Okay.
Yeah.
Okay, so what would the graph look like if it wasn't a value? And we went through all of it and looked at the graph where it was now.
I think I got one coming up for you. Right here. Alright, so now this is what we call a, does anybody remember?
It's the
Piecewise, yep, piecewise function. So now, first of all, this says, if x is less than 0, I'm going to graph 1 over x. So now, x is less than 0, a value less than 0. First of all, I plug in 0. What do you notice happens at 0? Undefined, right? Okay, and so then 1 over x. So less than 0 would be like -1. So what is at -1? What will it be? -1. Now, for those who wonder, where did we get that? If x is -1, I take 1 divided by -1. If x is -2, what do I get? -1/2. If x is -3, what do I get? -1/3. Okay, so now let's think, okay, I need to know what does the graph do here? Okay, so let's pick a value in between 0 and -1. Let's try -1/2 or -0.5. What is 1 divided by -0.5? What is 1 divided by -0.5? So that's going to be at -2. So do you kind of see the trend? What do you think the graph is going to do? It's going to go down. And remember, at 0, it was undefined. So 1 over x, and that's what you could actually do. We could graph 1 over x on your calculator. And if you graph it on your calculator, you will see that the left part of the graph does, in fact, look like this. So when in doubt, that's a way you could always check it. Now we have the right part of the graph. The right part of the graph says f of x equals x if x is greater than or equal to 0. So that means you start at what value of x? What value of x do I start this second one at?
0.
0. So if x is 0, I know y is 0. And I'm going to include it, so I'm going to use a closed circle. If x is 1, what is y? 1. If x is 2, what is y? 2. So that is what this graph here looks like. This is the right part of the graph. Okay? The left part of the graph was the 1 divided by x. The f of x equals x is the right part of the graph. So this is what the whole graph looks like.
You just put in random numbers.
Yeah, just put in random numbers. That's all we're doing. Now, this is an example of what you were just asking. You were just asking what happens if you get a value. Well, at 0, I get a value. It's 0. But if you look at the graph is definitely not continuous.
But when I typed in x on the graph, it went all the way into this.
Right, but that's why you have to look at this here. Okay, this is a piecewise function, which means we're taking part of this first graph, that's what we did in purple, we're taking the left part of that graph and we're combining it with the right part of the other graph. So this is one that if I were to plug in 0, I'm going to get a value of 0, but clearly you can look at the graph and see it's not continuous. If you were to walk along this, you're going to have to jump or hop. There's no way it'll work. Okay. Alrighty, so let's look at this. It says determine whether each function is continuous, once again. If discontinuous, identify the type of discontinuity as either removable or non-removable. Your calculator is your best friend for these. Okay? Your calculator is your best friend on these. So first of all, is that going to be continuous at 1? That's what we need to think. Is it going to be continuous at 1? Why not? Right, because if I plug in 1 right here, I get 1 over 0. So as a result, you know right away it's discontinuous. Okay, because you can't have 1 divided by 0. So let's go ahead and graph it, see what you get. Okay, what does it kind of look like? Yeah, it kind of looks like the 1 over x. Okay, and so
Is this what was included last? What? Oh, I don't know.
I'm not lost in that.
Because that's the only kind of time I'm doing a lot.
Okay, so let's go ahead and let's look back at the graph. What's going to happen is, if you are to graph this, and when you graph this on your calculator, you're going to notice here at 1, the graph splits. The graph here on the left goes down, and the graph here on the right goes up. Now at 1, we have what's called an asymptote. That asymptote is like an invisible boundary. I like to think of an asymptote as a electric fence. You don't want to touch it, otherwise you'll get shocked. So what this graph does is this graph gets as close and close and close as it can to that, but it will never touch that invisible boundary or that electric fence. And so in looking at that, I need to classify this. First of all, it's not continuous, so no, it's not continuous. Is this discontinuity removable or non-removable? Why non-removable? Yep. There's no way you can remove the discontinuity with just one little dot. This was the big hot one when we did that on site.
If it keeps getting closer and closer, it can't eventually, won't just touch it?
No, it won't. It will not touch.
There's like a point right
There's just, it will keep going on, it keeps going to infinity is what it does. But it never ever touches that point.
Ever.
Ever. Ever, ever. Okay, so let's go ahead and look at this one. This one actually has 2 discontinuities, so we need to evaluate it at each. Okay? We need to determine, is the graph continuous at 3? Is it continuous at -3? So we're going to break this into 2 answers. Okay, so first of all, we're going to look at x equals 3, and then what we'll do is we'll go through and do the same process for -3. So first of all, is the graph continuous at x equals 3? Yes or no? No, why not? Yep, when I plug 3 in here, I get 3 squared minus 9, which is 0. So is the graph continuous? No. Let's go ahead and do that for -3. Is it continuous at -3? No, for the same reason. So now let's go ahead and graph this. Now be careful when you graph this that you use
Yeah, I forgot where the fraction.
y. Yeah, I just did the division sign.
Interesting.
Or you can do the alpha y equals, and then that will do that as well for the fraction.
Oh, that's the
Whoa,
Oh, baby.
Just like it's moving.
So what'd you get?
It's like this.
Just straight up line left and then like it comes down and like Nike swooshes out.
So x plus 3 over x squared minus 9. I got mine a little different than that.
So did I.
Your last one is different too.
That's what I have.
What do you
This is
have?
what you have.
Okay, what I want you to do real
Oh,
quick,
this what you got?
what I want you to do real quick, okay? And what I'm going to do is I'm going to go ahead and stop the video. I'm getting close to time. What I will do is pick up the video again, but we're going to look at this more in depth, so I'm going to go ahead and bring it up on the big screen on the calculator. So,